Hi, welcome to Unit 7. We're talking about conservation of mechanical energy. This unit's a step along the path towards the granddaddy of all conservation laws, which is the law of conservation of energy. So you should be especially concerned about what this law says. The total amount of energy in the universe is constant. Put in other terms, you could say you can neither create nor destroy energy. In other words, energy is conserved. The basic definition of energy is the ability to do work. The ability to do work. And it comes in many forms. Just to name a few, light is energy. Heat is energy. Nuclear is energy. Kinetic energy. There's hydroelectric energy. Electric energy, solar, the list could go on. We could put geothermal. Sound is a form of energy. Chemical energy, potential energy, wind, and it just goes on and on. You could name a lot of different forms of energy. You can neither create nor destroy any of these forms of energy, but you can transform energy from one form to another. For instance, let's trace energy from a nuclear power plant to the light bulb that's hanging above your desk. So we're starting with nuclear energy. Nuclear energy within the atom is transformed into heat energy, which heats water into steam, which turns a giant turbine with kinetic energy. This cranks a generator, which is designed to produce electrical energy, which travels to your home and makes the filament of the light bulb. Let's pause there. The light emitting diode, because almost all of our lights now are LEDs, makes the LED of the light bulb give off light energy and heat energy. The new LED bulbs are much more efficient than the older incandescent bulbs with the filament. And just as a side note, they put off the same amount of light, but an incandescent bulb spends a very large amount of energy making heat. And LEDs make very little heat. So most of the energy savings is because of the saving the heat energy. So the energy from the nucleus of an atom took on many forms on the way to your desktop. Energy was not created, nor was it destroyed. It just changed forms, which leads us to a second definition. Energy is the ability to do work. Work is transforming energy from one form to another. Work was done when the nuclear energy turned into heat energy. Work was done when the electrical energy was changed into light energy. The amount of work done equals the amount of energy that was transformed. The amount of work done is equal to the amount of energy transformed. In this unit, we mainly study two types of energy and how they are transformed from one to the other. The first one is kinetic energy. This is the energy of motion. The other one is potential energy. This is energy due to an object's position above the earth. So if you think about an object sitting on the floor, it has very little energy, very little potential energy, because it's positioned above the earth, it's flat on the ground. But if you have a shelf up here, an object on top of the shelf has a lot of potential energy because it has the potential to fall. If we define energy as the ability to do work, think of that work as turning a paddle wheel, like in a mill. So here's the paddle wheel. It has the ability to spin in circles on its axis, which will be right in the middle. This represents some sort of energy that causes the paddle wheel to turn. So this object has kinetic energy. Since it has kinetic energy, it has the ability to turn the paddle wheel if it hits the wheel. Since you can neither create nor destroy energy, the moving object loses some of its kinetic energy so that the wheel can turn. Here's another instance with a paddle wheel. An object on a shelf, here's the shelf, here's the object, has the potential energy and can turn the paddle wheel if it falls from the shelf. The object on the shelf loses some of its potential energy because it was transformed into the kinetic energy of the wheel. So we can look at three different ways that work is done. One, exerting a force on an object, moving the object a certain distance. The second option, changing the kinetic energy of an object. For instance, this might be pushing an object. We are giving it motion, therefore it is kinetic energy. Or you can do work by changing the potential energy. Potential energy is due to position above the earth, and this would be something like lifting an object. Our first physics formula for work and the definition of work. Work is force times distance. In a formula, work, which is a capital W, equals capital F for force and lowercase d for distance. Work equals force times distance. Example A, the frictional drag on a cart and the floor is 20 newtons, so a force greater than 20 newtons is needed to make the object move from rest. But once the object is moving, a force of 20 newtons will keep the cart rolling in uniform motion once we overcome the initial friction. All we have to do is match the friction. 20 newtons will keep us in uniform motion. How much work is done by Marvin in exerting the force of 20 newtons while the cart moves down the hallway 6 meters? So let's start with our formula. Work equals force times distance. So we are exerting a force of 20 newtons over a distance of 6 meters for a grand total work of 120 joules. Newtons times meters give us a joule. How much work did Marvin do? Here it is, 120 joules. How much chemical energy was expended by Marvin's body? 120 joules. Remember, we didn't create energy, we didn't destroy energy, we just changed it from one form to another. The chemical energy in the body turned into the work that Marvin did on this object. The energy expended by Marvin can't just disappear. Because of friction, most of the energy is actually changed to heat energy, to be considered in detail in the next unit. Example B, 400 joules of work are done by a weightlifter in lifting 500 newton set of barbells. How far did the lifter lift the weights? Again, work equals force times distance. We know how much work that this lifter did. It was 400 joules. And the force required to lift a 500 newton set of barbells is 500 newtons. And we want to know, how far did this lifter lift the bar? So we've got 400 divided by 500, and that tells us that the lifter moved the barbells by 0.8 meters. Our first formula for work says that we can sweat and moan and sweat and groan, but if the object doesn't move, we did no work. So I'm going to put a question mark here, because if you're sweating, it certainly feels like you're doing work. But according to the formula, we did not move the object, we did not do any work.